All right, so two more things to illustrate on the diagram before we go back to the slides. So we say the chain may grow or shrink dynamically, right? So here, dynamically is very important feature for the linked list that's different from array. So let's now have some conceptual idea about why this is the case, okay? So let's talk about the case of shrinking, shall we? Over here, shrinking. And let's consider how to shrink a linked list versus shrinking an array. Let's talk about the array case first. Remember last week we spoke about how you can grow the array just by one element, and you will actually have to allocate the memory for a strictly larger array and then copy over all the elements to the corresponding position using two loops. Basically, that's what we did, right? You do something very similar in the case of deleting. Let me sketch that, and then we'll see. So let's say we got an array A over here, and then it's simply of size. What about 4? Okay. So we got 0, 1, 2, 3. Okay. Let's say conceptually all the elements over here are pointing to some objects. Let me simply just use different colors for the pointer just to say they are pointing to different objects, right? I don't really need to draw the objects themselves. Let's say index 0 pointing to some objects, index 1 pointing to another object, and also index 2 pointing to another object, and finally index 3 is pointing to another object, right? So we got 4 elements in the array. Let's say we want to delete, we want to shrink the size of the array by removing the elements at index 1. Let's say that's what we want to do. You simply just cannot just say, rather than letting A1 pointing to here, this object here, you'll simply let it point to null. That would not be an acceptable solution because in that way, you're creating a null slot in the middle of the array. So that would be unacceptable. That's not what we want. So what we want to do instead is, let's say what we want to do is we want to say we want to delete or to shrink the array index 1 elements. So we can simply just create some temporary array. Let me just call it temp. And then that array over there is going to be of size exactly one element fewer, right? Rather than size 4, it's going to be size 3. And then we're going to have 0, 1, and 2, right? And the idea would be for elements before index 1, we can simply copy them into the corresponding slot, right? And because of reference aliasing, we can simply say we'll simply let index 0 point to the same objects as A0 is pointing to, right? You can see they're pointing to the same objects. And for index 1, it is the one we want to delete, so we simply don't copy that. And then what about the rest? For the rest we'll simply just need to say, since we want to delete this one specifically, so for all the indices to the right of that deleting that index to be deleted, we want to shift their position just to the left by 1 position, right? You can think about index 2 conceptually is going to be shifted to the left by 1 position. Index 3 is going to be shifted to the left by also 1 position, and depending on how many such elements there are. So that's why you have to use a second loop to really handle this, right? To copy everything to the left of the index to be deleted, you need a first loop. And to copy all the elements to the right of the index to be deleted, you need a second loop. So you need 2 loops, but they are not really nested. They're simply one after the other. So that's why overall, shrinking the array will still be linear, right? That's something I just want to remind you. Okay, let me just finish the diagram just for completeness. So we don't worry about this part anymore. So what we'll need to make sure is we actually copy whatever this address is into here, and also whatever this address over here into here. And notice copying from index 2 into index 1, index 3 into index 2, right? So when you write a loop, to really implement this, you got to be careful, right? So that means this index 1 is actually going to point to the same objects, and also index 2 is also going to point to the same object, right? It's a conceptual sketch. And it will definitely be linear, because at the end, you can actually say A would be reassigned to this particular temporary array that we simply just reassign, right? Eventually, that's what we'll do. Right, so that's the steps that we involved in shrinking the array, which would be asymptotically big O of n, which is expensive. And this will be the shrinking for the array. What about the shrinking for linked list? You will be surprised. It's actually incredibly cheap. Well, of course, I'm hiding some details, which I will only mention when we get to the code. But let me just describe one scenario to you. Let's say we want to delete the nodes, index 1 over here, right? We used to want to delete index 1. Let's say we also want to delete index 1 over here, right? In this special case, you can see index 1 happens to be the next node of the head, right? In that case, if I just want to delete this particular node, all I need to do is I just conceptually I want to get rid of this. In that case, what should be the new next node of the head? It should be whatever the old next of the node being deleted, right? So that means this pointer should be pointing to this node instead. That's the only thing I need to do, right? All I need to do is whatever this node to be deleted, whatever its next node is, I want to copy its address into the previous one, well, the head over here. That's what I need to do, right? The exact coding, you can think about how you might do this in Java, but we'll see that later when we see the Java code, right? So all I need to do is, let me just use maybe orange over here. So all I need to do is, I want to say, rather than pointing to over here, and also this next node reference should also be deleted, it is actually going to point to just this node over here. That's about the deletion procedure, like a shrinking procedure. And would that be linear? The answer is no, because all we are doing over here is just to reassign the pointer over here. So assignments is a primitive operation, and we're only doing, you can think about we're doing 1 over here, and also assigning this to null over here, right? So that'll be a constant number of times. So in this case, it would be big O of 1, right? So big O of 1 would be for linked list. And also for big O of n, it will be for array. That's something I would like to just mention first, but we'll definitely revisit this more concretely in terms of code later. All right, finally, I would like to talk about the tail feature for linked list, right? We'll talk about the head, and I want to talk about tail as well. You can think about tail, if you really want to use it, it will be kind of convenient for like a trading space, actually, for time. That's something we'll also talk about later in the lecture. But let's say if you really want to have the tail, it's like a dedicated reference pointing to the end of the list. What about in case number 1? What will be the tail? Well, since there's no node actually in the list, so that means like for the case of head, tail will also be just simply null. That'll be easy for case number 1. What about case number 2? When there is only one node in the linked list, in that case, that node should be the head and the tail at the same time. So that means the tail will also be pointing to the same node, right? So far, it's straightforward. What about case number 3? We got definitely the head node, and we got the last node, and we got arbitrary number of nodes in general in between. In that case, we definitely want to make sure somehow the tail is pointing to the very last node, whose next reference over here is actually null, right? So there's only one node whose next reference will be null in the singly linked list, in which case it would be just the last node, which will be the tail, right? And if you do decide to actually include tail as an attribute in your singly linked list, in that case, you have to make sure every time if there's any operation, especially mutator, you want to implement for the singly linked list, you want to make sure the head and tail are always updated properly. Otherwise, for example, let's say this. If I actually try to delete, let's say for example, let's say if I try to delete this particular node over here, if I do it, in that case, after deleting this, that means this particular currently this node, its next reference will just become null after I delete this node, right? In that case, there's only one node left, in which case, tail pointing to this node that has been deleted is not correct, it's not accurate. So tail instead should be pointing to this node as the new tail, as an updated tail. That's something you want to also keep in mind conceptually, right? There's lots of detail for you to really look after. That's why linked list, in some way, it's actually more tricky to get right than the arrays. But at this level, you definitely should really learn about how to do such problems, right? We'll definitely go over the basics, make sure you understand very well, so you can solve the more advanced one creatively yourself. Let me go back to the slides and let's see what else. Right, so we have covered all these points again visually, right? And the last node, as I mentioned, is a very special node. That's the only one whose next reference over here is going to be null, right? That's the way for us to tell whether we are reaching the end of the list. So maybe, for example, we can stop the iteration if we are running a loop. You'll see many algorithms on the linked list is like that. All right, let's now go over one more slide, and before we actually move on to Java coding, right? Very quickly. So due to the chain structure, as we explained, a singly linked list, when first being created, it does not need to be specified with a fixed length, right? So if you remember what happened in the case of array, let me write it down here, for example. If we have an integer array, let's say, so you would say integer array A, syntactically, you are required to actually say here, I say integer here, and then this part over here is going to be some number you have to put in, right? So that'll be the fixed length of the array. And of course, we know that if you really want to resize the array, either to grow it or to shrink it, it's going to be a linear time, especially when you, in particular, when you actually need to implement some loop to copy over the existing contents, right? So that'll be the limitation for the array. But on the other hand, in the case of the linked list, it's completely flexible. You start with something that's completely empty, and then you can add as many nodes as you like every time. And you're only bounded by not some prefix, like a preset size over here. You're only bounded by the memory of the particular computer you have, which means you're basically unbounded. Given that memory, you can almost say that memory is really unlimited. Okay. Right, so that's about the fixed length. But let me just give you again some heads up for array resizing. Right, we know that given that array is actually fixed length, so it would be expensive to actually do resizing of the array. So later on, we're going to talk about, maybe in the next lecture, we'll talk about there are two common strategies for resizing an array. Whenever it got filled out, it got filled out for all the content, it's basically full. There are two possible strategies, and we want to analyze their running time, or specifically average running time, to see which one will be the resizing strategy to go. If you really choose to use the array, resizing is really unavoidable. You just have to deal with it. In the previous courses, in 2030, or maybe in the first year Java course, you don't really have to worry about resizing, but now we have to worry about it. Okay, we'll get there later. All right. And we can say we can use a singly linked list to dynamically store and manipulate as many elements as we decide without the need to resize, right? So here are simply some example operations. So these are all the operations that we're gonna learn. Okay, I'm gonna walk you through the solution for some of them, but for the remaining ones, they will be assigned to you as exercises, which I highly recommend you actually finish them, right? Just to make sure you can master the basics. For example, you may just want to create a new node and set the relevant references. That's something we'll definitely go through. It will be the next part of the module. And whenever you want to delete, you want to insert or delete some node, either insert into or delete from, it can be different parts of the list. It can be the beginning, it can be the end, or it can be the middle. And the running time depends on which one you're doing. So we're going to talk about it. And then also the implementation detail are also different, right? Again, I'm going to give you the solution for some of them, but you have to really practice the remaining ones yourself. That'll be the best for your learning, I hope. And so let's now talk about this important point. Contrary to the arrays, how does linked list work? We do not keep track of all the nodes in a singly linked list directly by indexing the nodes. That means we can only indirectly find out where a node is based on its index, right? Now let me just revisit the point. In the case of the array, if I want to go to index 2, well, just go there. Just say A at index 2. Go there with a constant cost. Easy, straightforward. On the other hand, if I want to go to index 2 of a linked list, in that case, I cannot simply go there directly because dynamically there might be arbitrary number of nodes in the linked list, in which case we simply don't have the reference for each one of them. So the best we can do is to start from the head and then simply follow through the next reference until we reach that particular node's index, and then we know that we are there. That's the indirect way of finding where the node is based on its index, right? That's a very important point to keep in mind. All right, so this is just another linked list over here. It's basically just a linked list storing the city names. I believe that maybe Los Angeles, Mississippi, Atlanta, and also Boston, right? But the important point is here. You can see we got one reference to the first node called the head. We got one additional like a reference to the node called Boston, to the last node called tail over here. And then you can see for the last node, its next reference is simply just null, right? Oh, by the way, there's something I mentioned before called reference aliasing. Do you see any reference aliasing over here? I see at least one instance of reference aliasing. What's really reference aliasing? Right? I'll write it down maybe later in the Java code, but can you just recall very quickly what's reference aliasing? Pause the video and tell me. All right. Reference aliasing simply means an object's address is stored in multiple variables, meaning that diagrammatically, two arrows may be pointing to the same objects, basically, right? In this diagram over here, do you see any reference aliasing? Well, indeed, right? This and this arrows over here, they point to the same objects. Similarly, you can see over here, we also got reference aliasing in this diagram, right? So after the earlier deletion, right? So now you can see this particular node are being pointed to by two variables. One is the tail, because it is the last node. And the other one is the next over here, because the next of the head is actually pointing to this node, right? Let me write it down. It's also very important for you to note this. Reference aliasing. Okay, let me just write it down properly. If you cannot really grasp the idea from the earlier years about reference aliasing, you definitely want to make sure you understand, because without understanding reference aliasing truly, you just cannot master linked list. They definitely go very closely with each other. So in this case, what I want to do is, you can see here, the next reference of the head and also the reference for the tail, they point to the same objects, right? So if you try the following Boolean condition, you can definitely try this. If you try to compare tail over here to see if it is equal to, and now I can simply go for the head. Or let me use maybe darker blue over here. So if I try the head, and I can simply just say next just for now, right? There should be some public accessor for me to do that, but for now that's okay, right? So now you can see what I'm doing here. Tail pointing to here, head is over here, dot, look up the address of head, and we are going to this particular node, and then dot next. So go to the next, it will be pointing to this particular node over here. So these two references are pointing to the same node objects. That's why it's reference aliasing, right? So this expression over here, if you write it in Java, is actually going to evaluate to true. Right? That's something I would like to add as well. But we definitely need to revisit this once we see some concrete code. But if you got the idea, good for you. Alright, and then so some exercise over here only mentally. You don't need to write any Java code for that. We're going to do that from scratch from the next part of the video. But I want you to say, if you want to do the exercises over here, I got two of them for you. So you want to think about, for these two operations, basic operations on the linked list. One is to count the number of nodes currently in the list. And the other one is, how can you find out the reference to its tail? Well, let's say the tail, you don't really have the extra attribute tail. Let's say you only got the head. How would you do that? You can simply maybe use this diagram I already drew. All right, over here. Sorry, let me undo. Let's say this diagram over here. So if I want to calculate the size, right, I need to maybe initialize some counter to be 1 over here. Every time I have a next node to really go through that's not null, I should really increment the counter by 1, right? That'll be the idea. And how do I get to the tail? Let's say that this attribute doesn't exist. In that case, I have to maybe somehow keep using the next reference until I can see the next reference is actually null. In that case, I know I have found the tail, right? But what will be the running time? That's really important. Will the running time be constant or linear? Right? That's the question. Right? If you don't know the answer, I can tell you it's linear, but as to exactly why, let's now we'll save the discussion until we actually get to the coding. All right. So that's about what I want to say for the intuitive introduction to the linked list. Hopefully the diagrams actually help, and also some bullet points to summarize about the important features of linked list also help. I would say later on, once we finish coding the basic operation of the syncly linked list, come back to these two slides I just went over with you, and make sure you can then appreciate more about all the bullet points and insights I just discussed in this video.